Welcome back to the deep dive. Today, we're really getting into the weeds, tackling CISSP Domain-8, software development security.
Yeah, this is a big one.
It really is. We're shifting focus here, moving beyond just firewalls and network defenses.
Right. We're looking inside the applications themselves.
Exactly. How do we build security in from the absolute beginning? From, the first idea all the way through to code hitting production.
And maybe even beyond that into continuous delivery.
Absolutely. So the mission for you, our listener, is really to grasp what goes into providing genuine assurance for software.
That word assurance is key. When we use it in a security context, we're talking about confidence.
Confidence that the software does what it's supposed to.
Yes, and crucially, that it doesn't do what it's not supposed to. It means confidence that it's free from vulnerabilities, whether they got there by accident or someone put them there intentionally.
Okay, so it's not just bug hunting.
Not at all. It's about building trust, architecting security right into the core design.
We've got a lot of ground to cover today based on our sources. We'll be looking at how development methodologies have evolved, with security in mind.
And testing, obviously.
Yeah.
Different types of testing.
Right. Critical testing methods. And then the core vulnerabilities themselves, the OSP top 10, things like that.
Can't forget supply chain security either. That's huge now.
Definitely. Okay, so let's kick things off right at the start. Integrating security into the software development lifecycle, the SDLC.
The fundamental principle here, really, is that security has to be part of the process from day one. You can't just sprinkle it on later like some kind of magic dust.
Bake it in, don't bolt it on. I hear that phrase a lot.
That's the one. So you take the traditional SDLC phases, requirements, design, implementation, testing, operations, maintenance, security, needs to be an explicit consideration in all of them.
It's not just a testing phase thing.
Definitely not. In fact, guidance, especially from places like NIST, really emphasizes specific security steps before you even write a single line of code.
Right, like planning for security up front. It's about managing risk proactively, isn't it?
It absolutely is. So before you even finalize what the software is supposed to do, you've got two big tasks. First, you draft a security plan.
Okay, what goes into that?
Think of it as the roadmap for all security activities. It ensures things like threat modeling, code reviews, penetration tests, all that stuff are actually planned for, budgeted, scheduled. It guarantees they happen throughout the lifecycle.
Got it. And the second task?
Conducting a sensitivity assessment. This is maybe even more foundational. You have to know what kind of data this system will handle.
Because that determines how much security is enough.
Precisely. It drives the whole level of rigor. This is where you see those privacy risk ratings come in P1, P2, P3.
Tell us a bit more about those ratings. What do they signify?
Sure. So a P1 rating means high privacy risk. Think systems storing tons of sensitive, personally identifiable information, PII, or doing complex, ongoing data transfers. Big target, lots of potential harm if breached.
Okay. And P2?
P2 is moderate risk. Maybe it involves a one-off user-initiated transfer, perhaps anonymous. Still needs protection, but the scale of risk is lower.
And P3 is the low end.
Right, P3 is low risk. Minimal or no real privacy impact. Understanding if you're building a P1 system versus a P3 system. That radically changes everything. The budget, the controls, the testing intensity.
So if that initial assessment screams P1 high risk, then the security requirements for design, implementation, testing, even how you eventually scrap the hard drives during disposal, all of that has to be dialed up accordingly.
Exactly. Security dictates the requirements and the budget, not the other way around. Ideally, anyway.
And assuming you follow this process correctly, embedding security all the way through, eventually you get to the point where the system is built and tested. What happens then administratively?
Right. This leads us to a really important distinction, especially for anyone studying for the CISSP exam. The difference between certification and accreditation. They sound similar, but they're very different beasts.
Okay, let's clarify that. What's certification?
Certification is the technical deep dive. It's the hands-on evaluation to verify that the system security controls, the hardware, the software configuration, everything actually meet the documented security requirements. It asks, did we build it right technically?
So it's the proof that the security features work as designed.
Pretty much. Now, accreditation is different. That's the management sign-off. It's the formal, often legal approval from senior leadership to actually operate the system.
Ah, so it's not technical, it's about acceptance.
Exactly. The critical part is that accreditation signifies that management has reviewed the residual risk, the risk that's left over, even after all the security controls identified during certification are in place. and they have formally accepted that remaining risk on behalf of the whole organization.
Wow, okay, that's a huge difference. Certification proves the tech works. Accreditation means the bosses accept the leftover risk.
Correct. And that acceptance often comes with serious legal and financial responsibility. It's the point where leadership says, okay, we understand the remaining dangers, and we're willing to live with them to get the business value.
And that decision probably influences whether the system gets ongoing funding for maintenance and security updates too?
Often, yes. It's a major milestone.
Okay, so that's the sort of traditional structured NIST approach. But, the business world moves fast. That demand for speed really challenged these older, more rigid models, didn't it?
Oh, absolutely. The classic waterfall model, for instance, feels almost ancient now in many contexts.
Describe waterfall for us. Linear, right?
Very linear. You finish one phase,
Yeah.
completely requirements before you even start the next design. Then you finish design before starting implementation and so on. Step by step, very sequential.
What's the upside?
It's highly structured, predictable, great if your requirements are absolutely set in stone and won't change, maybe for like building flight control software or something safety critical.
But the downside?
Rigidity, huge rigidity. If you discover a flaw in the design phase after you've started coding, going back is incredibly painful and expensive. Our sources mention even the guy who proposed it, Dr. Royce, quickly saw the need for some feedback loops. But fundamentally, it's slow.
Yeah, you could build something perfectly to spec, but by the time it launches, the business need has totally changed.
Exactly. That frustration is what really fueled the move towards more iterative approaches, like the spiral model.
The spiral model seems interesting because it builds in risk analysis repeatedly.
It does. Think of it as doing mini waterfalls in loops or spirals. Each loop involves planning, explicitly analyzing risks for that iteration, doing the engineering work, and then evaluating the result before planning the next loop.
So risk management isn't an afterthought. It's baked into every cycle.
Right. It forces you to constantly think about what could go wrong, which helps avoid those massive late-stage surprises.
Okay, and contrasting with that, there was also rapid application development, or RAD. That sounds like it's all about speed.
It is. RAD is laser-focused on getting something functional in front of the business users as quickly as possible. It relies heavily on rapid prototyping and really intense, continuous feedback from the customers or users.
Less about a grand plan, more about quickly meeting immediate needs.
Exactly. Less formal documentation, more working prototypes. Heavy user involvement is key.
But the dominant paradigm today, the one everyone's talking about, is Agile.
Definitely. And it's crucial to understand Agile isn't just one specific process, like Scrum or Kanban. It's more of a philosophy, really.
A philosophy based on?
4 core values laid out in the Agile Manifesto. These really flick traditional thinking on its head.
Okay, what are they?
First, individuals and interactions over processes and tools. People talking matter more than rigid workflows. Second, working software over comprehensive documentation. Get something functional, don't just write about it.
Makes sense. Keep going.
Third, customer collaboration over contract negotiation. Work with the customer continuously, don't just stick to the initial contract terms. And fourth, responding to change over following a plan. Be ready to adapt when requirements shift, because they always do.
So flexibility, communication, working software, adaptation, that's the essence.
That's the core idea. It's about delivering value quickly and being able to pivot.
And in practical terms, how does Agile manage requirements? Not big documents, right?
Right. The primary tool is the user story. It's a simple format.
Give us the template.
As a type of user, I want to perform some task so that some goal is achieved.
Okay, as a shopper, I want to add items to my cart so that I can purchase them later. Like that.
Exactly like that. It frames every feature in terms of user value. And this structure naturally helps with validation, making sure you're building the right thing, the thing the user actually needs to achieve their goal.
This constant push for speed, for iteration, for getting working software out, it must have created friction between the different teams involved, right? Developers, ops.
Huge friction, traditionally. Developers wanted to push changes fast. Operations wanted stability, which meant resisting change. That conflict slowed everything down.
And that led to DevOps.
Precisely. DevOps is about breaking down those silos, combining development and operations teams, tools, and cultures to streamline the whole process. The goal is that smooth, fast pipeline for continuous integration and continuous delivery, CI/CD.
Okay, faster delivery. But what about security in that faster pipeline? You could just be shipping vulnerabilities faster.
And that's the critical point. That's where DevSecOps comes in. It's about integrating security into the DevOps pipeline, not leaving it as a separate final check.
So automating security checks within that CI/CD flow.
Yes, exactly. This is where the idea of shift security left really becomes practical.
Shift left, meaning involve security much earlier in the process.
Right. Get security involved during requirements gathering, during design, not just waiting until the testing phase. Security teams become partners, enablers, embedding automated checks and guardrails into the development workflow.
How does that work technically? How do you automate security checks in a pipeline?
A lot of it relies on software-defined security, or SDS. Just like networking infrastructure can be controlled via code in a software-defined network, SDN, security functions, firewalls, intrusion detection prevention systems, IDSDS, vulnerability scanners can also be configured and managed through code and APIs.
So you can script security policy enforcement.
You got it. You can automatically run a security scan as part of the build process. If the scan finds critical vulnerabilities, boom, the pipeline stops automatically. The build fails. Code doesn't get deployed until the security issue is fixed.
That sounds way more effective than relying on manual reviews done, once every few months.
It's a game changer for embedding security at scale and speed.
Okay, so organizations are adopting DevSecOps, automating security. How do they know how well they're actually doing? How do they measure their maturity in these secure development practices?
That's where maturity models come into play. The big general one for overall process improvement in development organizations is the Capability Maturity Model Integration, or CMMI.
CMMI. It has levels, right? 5 levels.
Yes, 5 levels. They describe a path from, well, chaos to continuous improvement. It's worth walking through them quickly.
Okay, level 1.
Level 1 is initial, basically chaos. Processes are unpredictable, poorly controlled, reactive. Success depends entirely on individual effort, heroics, as they sometimes call it. No real plan.
Sounds stressful. Level 2.
Level 2 is managed. Now, things are a bit better. Basic project management processes are established to track cost, schedule, and functionality. Requirements are managed. But crucially, these processes are often applied only to individual projects, not consistently across the whole organization. There's some repeatability, but it's project-specific.
Okay, so pockets of control, but not organizational standardization yet. That must be level 3.
Exactly. Level 3 is defined. Now, the organization takes the successful processes from level 2 projects and documents them, standardizes them, and makes them the organizational standard process. Everyone follows the same tailored process. It's proactive, not just reactive.
Getting more sophisticated. What's level 4?
Level 4 is quantitatively managed. This is where data becomes central. The organization sets quality and performance goals and then collects detailed metrics throughout the process. They use statistical analysis to understand process capability, control variation, and predict outcomes. It's data-driven control.
And the peak. Level 5.
Level 5 is optimizing. At this level, the organization isn't just controlling its processes, it's actively, continuously improving them. They use the quantitative insights from level 4 to identify bottlenecks and opportunities for improvement, and they pilot and deploy changes systematically. Think mature CI/CD, constant refinement. It's the pinnacle of process maturity.
That's a comprehensive model for overall development. But what if an organization wants to focus specifically on improving its secure development practices? Is CMMI the best tool?
It can help, but it's quite broad. For a security-specific focus, many organizations turn to the OWASP Software Assurance Maturity Model, or SAM.
Sam, how's that different?
SAM is built by security people for security purposes. It breaks down secure software practices into 5 business functions: governance, design, implementation, verification, and operations. Within each, it defines different activities and maturity levels.
So it lets you target security improvements more directly.
Yes. You can assess where you are in, say, security testing under verification or threat modeling under design, and then plan specific steps to reach the next level of maturity in those specific security areas. It's generally considered a better fit than CMMI if your primary goal is boosting software security maturity rather than general development process maturity.
All right, let's shift gears from the how of building software, the process, to the what, the code itself. Understanding some programming fundamentals is key here. Maybe a quick history lesson on programming languages?
Sure, it helps frame things. We talk about generations. First generation was machine language. Pure binary, ones and ors. Directly understood by the processor, but utterly unreadable for humans.
Painful. What came next?
Second generation. Assembly language. This was a huge leap. It uses mnemonic codes like ADD for addition, MOV for move data, and symbolic names for memory locations.
Uh-huh.
Still very low level, tied directly to the hardware architecture, but way easier than binary.
Still pretty niche today, right? Used for device drivers, embedded systems, maybe.
Exactly. The vast majority of development now happens in third-generation, high-level languages. Think C, C++, Scala, Java, Python, C#. These use syntax much closer to human language, abstract away the hardware details, and are generally processor independent.
Makes development much faster and easier. Now, within these high-level languages, there's a key difference in how the code actually gets run by the computer, right? Compiled versus interpreted.
Yes, that's a fundamental execution model difference with security implications. Compiled code is translated once, by a compiler program, into machine language specific to the target processor and operating system. The result is typically a standalone executable file, like a .exe on Windows.
So it runs fast because it's already in the computer's native language.
Generally, yes. The downside is that compiled code isn't portable. Code compiled for Windows won't run on a Mac or Linux without recompiling.
Okay, and interpreted code.
Interpreted code isn't pre-compiled into machine language. Instead, an interpreter program reads the high-level code line by line and executes the corresponding machine instructions on the fly every time the program runs. Think scripting languages like Python or JavaScript often work this way.
What are the trade-offs there?
Interpreted code tends to be more portable. The same script can often run anywhere you have the interpreter installed. It can also be more flexible for dynamic changes. But it's generally slower because of that constant translation step.
Now, Java did something clever here, kind of a hybrid approach.
It did. Java introduced bytecode. When you compile Java code, it doesn't create native machine code. It creates this intermediate, platform-independent bytecode.
And how does that run?
That's where the Java Virtual Machine, the JVM, comes in. The JVM acts like an interpreter for the bytecode. It takes the platform-neutral bytecode and translates it into the specific native machine instructions for whatever computer it's running on right at runtime.
Ah, so that's how Java achieves write once, run anywhere. The bytecode is universal. The JVM does the final specific translation.
Exactly. But there's a crucial security benefit to this JVM model, too.
Which is?
The Java sandbox. Because the JVM sits between the bytecode and the actual operating system, it can enforce strict security rules. It creates a controlled environment in the sandbox, especially for running potentially untrusted code, like Java applets downloaded from the web back in the day.
How does the sandbox protect the system?
It restricts what the code running inside it can do. It limits access to sensitive resources like the local file system, network connections, or system memory based on a security policy. If the code tries to do something forbidden, the JVM stops it. It's a containment mechanism.
Very important for running code from unknown sources. Okay, let's move into object-oriented programming, OOP. These concepts, encapsulation, cohesion, coupling, they're not just about organizing code, they have real security implications. Let's start with encapsulation.
Encapsulation is about bundling data together with the methods or functions that operate on that data into a single unit called an object. But the key part is controlling access.
Hiding the internal detail.
Exactly. It's often called information hiding. The internal state or structure of the object is kept private, hidden from the outside world. Other parts of the program can only interact with the object through well-defined public interfaces or messages.
How does that help security?
It reduces the attack surface. By preventing direct access to internal data, you make much harder for other parts of the program or an attacker controlling them to put the object into an invalid or insecure state. You maintain integrity through controlled interaction.
Okay, now for cohesion and coupling. These always trip people up. We want high cohesion and low coupling. What's cohesion?
Cohesion measures how focused a single module or component is. How many different kinds of tasks does it perform?
And we want it to be highly focused.
Yes, we strive for high cohesion. This means the module does one thing, or a small set of very closely related things, and does it well. Think of a module that only handles user authentication versus one that handles authentication and logging and database access.
Why is high cohesion good for security?
Highly cohesive modules are easier to understand, test, maintain, and secure. Their purpose is clear, their interactions are limited. Low cohesion modules, doing many unrelated things, become complex spaghetti code, hard to reason about, hard to test thoroughly, and easy places for vulnerabilities to hide.
Okay, so high cohesion, focused module. Now, coupling. We want this to be low.
Right. Coupling measures the degree of interdependence between different modules. How much does one module rely on or know about the internal workings of another module?
And we want them to be independent.
As independent as possible. We aim for low or loose coupling. This means modules interact through stable, well-defined interfaces and don't depend on the internal implementation details of other modules.
Why is low coupling important for security?
Several reasons. First, if modules are loosely coupled, a change or a bug fix in one module is less likely to have unexpected ripple effects, breaking other modules. Second, it reduces the attack surface. If Module A is tightly coupled to Module B, a vulnerability in B might be more easily exploitable from A. Low coupling promotes modularity and containment.
So high cohesion within modules, low coupling between modules. That's the architectural sweet spot for maintainable and secure code.
Absolutely. It makes a system more resilient, easier to change safely, and easier to secure.
All right, let's pivot to the data itself, which is often what we're trying to protect. Databases face some subtle threats beyond just, say, SQL injection, like aggregation and inference attacks. What's the difference?
They're both about deriving sensitive information from seemingly non-sensitive data, but they work differently. Aggregation is about combining multiple pieces of low-sensitivity data, often from different sources, to reveal a higher sensitivity fact.
Can you give an example?
Sure. Imagine you have access to individual anonymized sales records, low sensitivity. And you also have access to public reports on regional store performance, low sensitivity. By aggregating these, correlating the sales data with the regional performance, you might figure out specific, sensitive product sales figures for a competitor's key store, something considered highly sensitive. You combine pieces to build a bigger secret picture.
Okay, so aggregation is combining multiple inputs. What about inference?
Inference is about deduction. You use a single piece of seemingly non-sensitive information, or maybe even a lack of information, to logically deduce a sensitive fact. Let's say you query a personnel database for employees earning over $200,000 in a specific small department. If the query returns 0 results, you've just inferred that nobody in that department earns that much. Or if you query for a specific person's medical record and get an access denied error, you've inferred that such a record exists, which itself might be sensitive. You're drawing a conclusion based on limited data or system responses.
These sound tricky to defend against, especially in systems handling data at multiple classification levels.
They are. High-security environments, particularly multi-level security MLS systems used in military or intelligence, often employ a technique called polyinstantiation to counter inference attacks.
Polyinstantiation, what's that?
It literally means many instances. The database is allowed to store multiple records with the same primary key, like an employee ID, but with different data at different classification levels.
How does that help?
Imagine a top-secret project name, a user with secret clearance queries for projects. Instead of just getting access denied or no result for the top-secret project, which would let them infer its existence, the polyinstantiated database might actually return a plausible but fake project name at the secret level. It provides cover data to prevent inference about the higher-level information.
Fascinating. Creates ambiguity to mask the truth.
Exactly. It's a complex but powerful defense against inference.
Now, stepping back to more common database defenses, we mentioned a key technique earlier for stopping web attacks.
Yes, parameterization. Cannot stress this enough, especially for preventing SQL injection.
Remind us how it works.
Use parameterized queries, sometimes called prepared statements. Instead of building a SQL query string by concatenating user input directly into it, you use placeholders, like or named parameters, for the input values. The database engine then treats the input strictly as data. It's never interpreted as part of the SQL command itself. It effectively neutralizes the injection attempt.
A fundamental secure coding practice for database interaction. And finally, just to touch on it, the core principles that ensure database transactions are reliable. ACID.
Right. ACID is crucial for data integrity in transactional systems. It stands for atomicity. Transactions are all or nothing. Either all changes succeed or none of them do. The database is never left in a halfway state. Consistency. Transactions must bring the database from one valid state to another, respecting all defined rules and constraints.
Okay, A and C. What about I and D?
Isolation. Concurrent transactions shouldn't interfere with each other. The effect should be the same as if the transactions ran one after another serially, even if they're actually running in parallel. Durability. Once a transaction is successfully committed, the changes must persist, even if the system crashes immediately afterwards, e.g. written to non-volatile storage.
So ACID guarantees reliable transactions. Are there any security trade-offs with ACID?
Well, achieving strong isolation, especially serializable isolation, can be very performance intensive. particularly in highly concurrent distributed systems. It often requires locking mechanisms that can cause transactions to wait, creating bottlenecks. Sometimes systems relax isolation levels for better performance, but that can introduce subtle concurrency bugs if not done carefully.
Okay, we've talked about secure design and coding. Now, how do we check our work? Testing is obviously critical for assurance, but first, let's clarify two terms that sound similar: verification and validation.
Right, they're often confused. Verification answers the question, did we build a product right? Meaning, does it meet the specified technical requirements and design specifications? It's about conformance to the blueprint.
And validation.
Validation asks, did we build the right product? Meaning, does the software actually solve the customer's real-world problem or meet their actual needs? It's about fitness for purpose or utility.
So you need both. You could perfectly verify a product that completely fails validation because nobody actually wants or needs it.
Exactly. Verification without validation is useless. Validation without verification means you built something useful, but it might be buggy or insecure because it doesn't meet spec.
Got it. Now, the testing process itself usually follows a kind of pyramid structure, starting small and getting bigger.
Typically, yes. You start at the bottom with unit testing. This is testing individual small pieces of code in isolation, like a single function or method, to make sure they work correctly on their own. Developers usually write these.
Okay, testing the smallest building blocks. What's next?
Then you move up to integration testing. Here you start combining those individual units and testing how they work together. Do modules communicate correctly? Do their interfaces match up? You're testing the connections.
Makes sense. Units work. Now check if they play nicely together. After integration.
System testing. Now you're looking at the entire integrated system as a whole. Does it meet the overall functional requirements? Does it meet the non-functional requirements like performance, usability, and critically security requirements? You're validating the complete product.
And the final step, usually involving the customer.
That's user acceptance testing, or UAT. This is where the actual end users or their representatives test the system in a realistic environment to confirm that it meets their business needs and they're happy to accept it. It's often the final sign-off before deployment.
Okay, so unit integration, system UAT, that covers initial testing. But software changes, right? We add features, fix bugs. What kind of testing happens after modifications?
That's where regression testing is absolutely essential. Anytime you make a change to the software, add a feature, apply a patch, fix a bug, even change a configuration, you risk breaking something else that used to work.
The dreaded side effect.
Exactly. So regression testing involves rerunning a selection, or sometimes all, of your existing test cases, unit, integration, system test, after a change, and comparing the results to the previously known good results, the baseline.
To make sure you didn't introduce new problems.
Precisely. It's about ensuring the change had only the intended effect and didn't cause any unintended regressions in other parts of the system. It's vital for maintaining stability over time.
Okay, let's zoom in on testing specifically for security flaws. Application security testing, or AST. Two major categories here are static analysis and dynamic analysis. Let's start with static analysis, SAST.
SAST involves analyzing the application's source code, bytecode, or binary without actually running the program. It's like proofreading the code for potential security issues.
So it needs access to the code itself.
Generally, yes. SAST tools scan the code for known bad patterns, potential vulnerabilities like buffer overflows, SQL injection flaws, improper error handling, things like that. When humans do this manually, we call it code review. SAST automates much of that inspection.
What are the pros and cons?
Pro. It can find vulnerabilities early in the SDLC before code is even compiled or deployed, which makes them cheaper to fix. It can cover 100% of the code base. Con. It can generate a lot of noise, false positives, because it doesn't understand the runtime context. And it can't find flaws that only appear when the application is running.
Which brings us to dynamic analysis. How does that work?
DAST works by testing the application while it's running. It interacts with the application from the outside, like an attacker would, setting requests, probing inputs, analyzing responses, looking for vulnerabilities that manifest at runtime.
So it doesn't need the source code, black box testing.
Exactly. It's typically black box. DAST is great at finding issues related to the runtime environment, server configuration errors, authentication problems, session management flaws, and vulnerabilities that result from the interaction between different components.
Pros and cons of DAST.
Pro. It finds vulnerabilities that SAST misses, often with fewer false positives, because it confirms the flaw by actually exploiting it safely. It reflects the real-world attack surface. Con. It can only test the parts of the application it can reach or execute, so coverage might be incomplete. And it finds flaws much later in the SDLC, making them more expensive to fix.
So SAST and DAST are complementary. You really need both.
Ideally, yes. They find different kinds of vulnerabilities. SAST looks inside the code. DAST probes from the outside while it runs. Using both gives you much better coverage.
Okay, what about fuzzing? That sounds chaotic.
It kind of is in a controlled way. Fuzzing or fuzz testing is a dynamic testing technique where you automatically bombard the application's input interfaces with massive amounts of invalid, unexpected, or random data, the fuzz.
Why would you do that?
The goal is to make the application crash, hang, or behave unexpectedly. These failures often indicate underlying vulnerabilities, particularly things like buffer overflows, denial of service weaknesses, or failures in input validation and error handling. You're basically stress testing its ability to handle garbage input.
So it's good at finding those kinds of low-level corruption bugs.
Very effective for that, yeah.
Yeah.
Memory corruption vulnerabilities are often found through fuzzing.
And one more testing technique
Yeah.
mentioned in our sources, combinatorial software testing. What's the idea there?
Combinatorial testing is a more systematic, black box approach focused on efficiency. Modern software often has tons of input parameters and configuration options. Testing every single possible combination is usually impossible. It's called combinatorial explosion.
Right, too many possibilities.
So combinatorial testing uses clever mathematical techniques, like pairwise testing, to drastically reduce the number of test cases needed while still covering all important interactions between parameters. For example, pairwise testing ensures that every possible combination of values for any two input parameters is tested at least once.
So it finds bugs caused by the interaction of different inputs, but without testing millions of combinations.
Exactly. It's a smart way to get good interaction coverage with far fewer tests.
Yeah.
Much more efficient than trying to test everything or just picking combinations randomly.
Okay, let's talk about specific types of flaws these tests might find. Classic vulnerabilities. What about the backdoor or maintenance hook?
The back door. This is an undocumented way to get into the system, bypassing normal security controls like logins. Developers sometimes build these in during development for easier debugging or testing.
But they're supposed to remove them before release, right?
Absolutely. If a backdoor is left in the production code, it's a massive security hole. It gives anyone who discovers it, maybe a disgruntled former employee or an attacker, a secret way in, often with high privileges. Very dangerous.
And the one that really put vulnerability research on the map, buffer overflow.
Still a classic, especially in languages like C and C++ that allow direct memory manipulation. A buffer overflow happens when a program tries to put more data into a buffer, a fixed size area of memory, than it can hold.
And the extra data spills over.
Right. It overflows and overwrites adjacent memory locations. The danger is that this adjacent memory might contain critical data, like return addresses for function calls on the program's execution stack.
What's the impact?
By carefully crafting the oversized input, an attacker can overwrite that return address to point to malicious code they also injected as part of the input. When the function finishes, instead of returning normally, the program jumps to and executes the attacker's code, usually with the privileges of the vulnerable application. That's remote code execution.
The holy grail for attackers, still relevant today.
Very much so, though modern operating systems have defenses like ASLR and DEP that make exploiting overflows harder. But they still happen.
Okay, another subtle one. Time of check to time of use. TUCO CTUU. What kind of vulnerability is this?
This is a race condition vulnerability. It exploits the tiny time gap between when the software checks for a certain condition, like checking if a user has permission to access a file, and when it actually acts on the result of that check, like opening the file.
How can that be exploited?
An attacker tries to change the condition after the check but before the use. For example, the program checks if file.txt is owned by the user. Check passes. Then before the program opens file.txt, the attacker quickly replaces file.txt with a symbolic link pointing to a sensitive system file, like etc. for past. The program then opens the sensitive file, thinking it already checked permissions correctly.
Sneaky. Exploiting the timing gap.
Exactly. These are notoriously hard to find and fix because they depend on precise timing and the non-deterministic nature of multitasking operating systems.
All right, shifting from finding flaws to what happens after a flaw is found, particularly by independent security researchers. There is an ethical dimension here around vulnerability disclosure. What are the main approaches?
The two main camps are responsible disclosure and full disclosure.
Let's start with responsible disclosure. What does that involve?
This is generally considered the standard ethical approach. The researcher who finds the vulnerability privately contacts the vendor of the affected software, provides them with the technical details, and maybe a proof of concept exploit, and agrees to keep the vulnerability secret for a reasonable period.
To give the vendor time to fix it?
Exactly. The idea is to allow the vendor time to develop, test, and release a patch before the vulnerability becomes public knowledge. This protects the users of the software from attacks while the fix is being prepared. Once a patch is available, the details might then be released.
Okay, that sounds responsible. What's the argument for full disclosure then?
Full disclosure takes the opposite approach. Researchers immediately publish all the technical details of the vulnerability, sometimes even including working exploit code, publicly.
Why would they do that? It seems dangerous.
The arguments for it are usually, 1, it puts maximum pressure on the vendor to fix the problem quickly, especially if they've been unresponsive in the past. 2, the belief that security through obscurity, keeping flaws secret, is ineffective, and users have a right to know immediately if they are vulnerable.
But what are the downsides?
The huge downside is that it gives attackers, including less skilled script kiddies, immediate access to the vulnerability information and possibly exploit code before a patch is available. It creates a wide-open window for exploitation, potentially harming many users. The vast majority of the security industry now favors responsible disclosure for this reason.
So responsible disclosure balances getting the fix out with protecting users in the interim.
Yes, it's seen as the approach that best minimizes harm while still encouraging vendors to address security flaws.
To really understand the threats applications face today, especially web apps, the go-to resource is the OWASP Top 10. It lists the most critical web application security risks. Looking at the 2021 list, there were some major shakeups, right?
Huge shakeups. The most significant was what hit the #1 spot, A01, broken access control.
That jumped up from 5th place, I think.
It did. This highlights that failures in authorization, ensuring users can only access the data and functions they're actually permitted to access, are now seen as the most critical and prevalent web app flaw.
What kind of failures does that cover?
Things like insecure direct object references, IDOR, privilege escalation, missing function-level access control, often tied to misconfigured permissions in cloud services or APIs between microservices. Basically, the application doesn't properly enforce who can do what.
Okay, #1 is access control. What else changed significantly? Injection used to be #1.
Injection is still huge, but it gave broader and moved slightly down to AO3. Injection. The big change is that this category now consolidates several types of injection. It includes the classic SQL injection, NoSQL injection, LDAP injection, OS command injection, and it now officially includes cross-site scripting, XSS.
So XSS is now considered a form of injection.
Yes, under the broader umbrella concept. Untrusted data gets sent to an interpreter as part of a command or query, or in the case of XSS, sent to the user's browser to be executed. The root cause is the failure to separate data from commands or code.
Interesting consolidation. What about new categories? There was one entirely new entry high up the list, wasn't there?
Yes, and it's a really important one, AO4, insecure design. This is brand new in the top 10 and debuts at #4.
Insecure design. What does that mean? It's not about implementation bugs.
Exactly. This category recognizes that many security problems aren't just coding errors, bugs, but fundamental flaws baked into the application's architecture and design from the beginning. It's about missing or ineffective security controls that should have been designed in.
Like what kind of flaws?
Lack of threat modeling during design, insecure business logic flows, improper separation of duties in the design, storing sensitive data insecurely by design. To prevent this, OWASP emphasizes needing things like threat modeling and secure design patterns before you start coding. It's a call to shift left security thinking to the architectural stage.
That's a big philosophical shift. Okay, what else moved around? Sensitive data exposure changed.
Right. What used to be sensitive data exposure is now ASO2, cryptographic failures. This puts more focus not just on whether data was exposed, but why. Often it's due to failures in applying cryptography correctly, using weak algorithms, poor key management, not encrypting data at rest or in transit when it should be.
And broken authentication also got renamed.
Yes, it's now AO7, identification and authentication failures. This broadens it slightly to include failures in identifying users correctly, as well as classic authentication flaws like weak password policies, improper session management, or failures in implementing multi-factor authentication correctly.
One more complex one, AO8, software and data integrity failures. That sounds like it covers a lot.
It does. It's another consolidation category reflecting modern risks. It bundles together issues related to software updates, like insecure CI/CD pipelines allowing malicious code injection, critical data integrity checks, like protecting against malicious redirects, and, very importantly, unsafe deserialization.
Unsafe deserialization.
Yeah, that's where an application takes serialized data packaged up for transfer or storage, from an untrusted source, and rebuilds it into an object in memory without proper validation. Attackers can sometimes manipulate this serialized data to execute arbitrary code when it gets deserialized. It also covers risks from relying on third-party software components with known integrity issues, the supply chain aspect again.
Okay, so the OWASP list really reflects the modern complex threat landscape. Let's drill down into a few specific injection types that are always relevant. SQL injection first.
The absolute classic database attack. The attacker enters specially crafted input, often through a web form or URL parameter, that the web application mistakenly includes as part of a SQL command sent to the backend database.
Instead of treating it just as data.
Right. So instead of searching for the username admin, the database sees a command telling it to find the user admin and then ignore the rest of the query, the password check. This can let attackers bypass logins, steal data, modify data, even take control of the database server.
Still common.
Depressingly common when developers don't use parameterized queries.
Okay, now the client-side injection. Cross-site scripting, XSS. How does that work?
XSS involves injecting malicious scripts, usually JavaScript, into a web page that other users will view. The script then gets executed by the victim's browser in the context of the trusted website.
So the browser thinks the script came from the trusted site.
Exactly. This allows the script to do things like steal the user's session cookies, redirect them to malicious sites, deface the web page, or install malware. A common way this happens is through reflected input.
Reflected input.
Yeah, where a website takes user input, like a search term, and immediately includes it, unvalidated, back in the response page. If the input was script alert, XSS script, that script runs in the user's browser.
And there's a more dangerous type, persistent XSS.
Yes. Persistent XSS or stored XSS is where the malicious script is actually stored permanently on the web server, maybe in a database, like in a user comment on a forum or a product review. Then every user who views that page gets the script executed in their browser. Much wider impact.
Okay, one more tricky one. Cross-site request forgery, CSRF or XSRF. This one exploits the browser's trust.
It does. It's sometimes called a session writing attack. The attacker tricks a logged-in user's browser into sending an unintended malicious request to a website where the user is currently authenticated.
How do they trick the browser?
Maybe via a hidden form or an image tag on a malicious website the victim visits. The victim's browser automatically includes any relevant cookies, like session cookies, for the target site with the request. So the target site thinks the request is legitimate, coming from the authenticated user.
What can the attacker achieve with this?
They can force the user's browser to perform actions on the target site without the user's knowledge or consent. Things like changing their password or email address, making a purchase, transferring funds, posting content. It leverages the existing trust relationship between the user's browser and the target site.
Okay, these are serious threats. How do developers fight back? What are the core secure coding practices? We mentioned one already for SQL.
Parameterized queries. Absolutely #1 defense against SQL injection. Use prepared statements or equivalent mechanisms provided by your database framework. Never, ever concatenate user input directly into SQL strings.
What else? A general principle.
Validate all inputs. Assume any data coming from outside the application user input, data from other systems, configuration files, is potentially malicious. You need robust input validation.
What kind of validation?
2 types. Syntactical validity. Does the input conform to the expected format length character set? For example, is it a valid email address format? And semantic validity. Does the input make sense in the business context? For example, is the quantity ordered a positive number?
And what's the best approach to validation? Allow listing or block listing?
Allow listing, also called positive validation, is strongly preferred. Define exactly what is allowed. Example, only alphanumeric characters, only digits 0, 9, and reject everything else. Block listing, negative validation, where you try to list all the known bad inputs, is almost always incomplete and easily bypassed by clever attackers. Allow listing is much safer.
Good advice. What about seeing attacks as they happen?
You need good logging and intrusion detection. Log security-relevant events, failed logins, access control failures, input validation errors, unexpected exceptions. This allows you to detect potential attacks in progress or analyze them after the fact. Forensics.
Any security risks with logging itself?
Yes. You have to be careful what you log, especially in production. Verbose debug logs might contain sensitive information like passwords, session tokens, PII, or system details that can help an attacker if the logs are compromised. So tune logging levels appropriately for a production log, enough for security monitoring, but not sensitive details.
Makes sense. And finally, a general strategy for reducing risk.
Minimize the attack surface. Basically, reduce the amount of code and functionality that is exposed to potential attackers.
How do you do that?
Follow the principle of least privilege run processes with the minimum permissions needed. Reduce the number of running services or open network ports. Limit the number of entry points, APIs, web forms the application exposes. Disable unused features or modules. The less code an attacker can interact with, the fewer opportunities they have to find a vulnerability.
We touched on this earlier, but modern software development isn't usually about building everything from scratch anymore. It's more like assembling applications from pre-built parts, right?
Absolutely. Using third-party components, libraries, frameworks, modules, both commercial off-the-shelf, COTS, and open source software, OSS, is pretty much the standard way things are built now.
But that introduces a whole new layer of risk, doesn't it? The supply chain risk.
A massive layer. It's recognized now as a major enterprise risk, not just an IT problem.
What kinds of risks are we talking about in the cyber supply chain?
It's broad. It includes vulnerabilities within those third-party software components themselves. It includes potentially compromised hardware components. It covers risks from third-party service providers who might have physical or virtual access to your systems, or CodeThink outsourced developers or maintenance crews. Even poor security practices by suppliers further down the chain can impact you.
So how do organizations start to manage this complex risk?
It requires a strategic approach. Things like including specific security requirements in all contracts and RFPs with suppliers, requiring suppliers to demonstrate they have their own secure software development lifecycle processes, and, where feasible, trying to get source code access for critical purchase software.
Okay, let's focus on managing the software components themselves, the third-party components or TPCs. It's everywhere, COTS and open source. How do you handle the inherent risk?
The absolute first step is visibility. You have to know what you're using. This means maintaining an accurate inventory, often called a software bill of materials, or BOM.
A BOM, like a list of ingredients for the software.
Exactly. It lists all the TPCs used in an application, including their specific versions. There are tools now, software composition analysis, SCA tools, that help automate generating and managing BOMs. The SafeCode framework emphasizes this. Maintain a list. Unique IDs, map names, create the BOM. Why? Because you cannot manage what you do not know.
Right. If a new vulnerability, a CVE, is announced for Log4j version 2.14, you need to know instantly which of your hundreds of applications are using that specific version. Without a BOM, you're flying blind.
Precisely. So step one is the BOM. Step two is assessing the risk of each component on that list.
How do you assess the risk?
It's twofold. First, check for known vulnerabilities. Does the specific version you're using have any published CVEs against it? Tools can automate checking the BOM against vulnerability databases. Second, evaluate the operational risk related to the supplier or the open source project.
What do you look for in the supplier or project?
Things like, do they follow secure development practices? Do they use secure coding standards? How often do they release patches or updates? Do they have a clear process for handling security reports? How active is the maintenance community? A component with no updates in 3 years carries a very different risk profile than one updated last week.
Okay, so you've got your BINM, you've assessed the risks. What happens when you find a component that is vulnerable or unacceptably risky? What are the mitigation options?
The ideal and usually first option is to patch or update the version. If the vendor or project has released a newer, fixed version, update to that.
What if a patch isn't available, or the new version breaks compatibility with your application?
Then you look at option two. Replace the component with an equivalent. Can you find a different library or module that provides the same functionality but doesn't have the vulnerability or comes from a more trusted source? This might require some refactoring of your code.
And if replacement isn't feasible, the last resort.
The last, and often most painful resort, is to branch the code internally. This means you take the source code of the vulnerable open source component, if available, fix the vulnerability yourself, and then maintain that modified version internally.
That sounds like taking on a lot of responsibility.
It is. It creates significant technical debt. You are now responsible for all future maintenance, security patches, and compatibility updates for that component forever. It pulls your developers away from working on your core product. It solves the immediate problem, but creates a long-term maintenance burden. It's usually avoided unless absolutely necessary.
Okay, so managing TPCs is complex. Does the assessment approach differ between COTS and open source software?
Yes, significantly. For
Mhm.
COT software, you typically don't get the source code. So your assessment relies heavily on the vendor's reputation, their security documentation, any third-party certifications they have, like SOC2 reports, and public vulnerability databases. You're trusting the vendor's process, essentially.
And for open source?
With OSS, the source code is usually available. This means you can perform your own code reviews or run SAST tools on it, giving you deeper visibility. However, OSS usually comes as is, with no warranty or formal support agreement. You find a bug, you might report it, but there's no guarantee it will be fixed quickly or ever. You might have to fix it yourself, branching, or find an alternative.
So COTS is less transparent but comes with support. OSS is transparent but often without support guarantees.
That's a good summary of the trade-off.
What about software escrow? Does that help with assessing COTS security?
Not really for assessment. Software escrow is where a trusted third party holds a copy of the COTS application's source code. The code is released to the customer only under specific, pre-agreed conditions, typically if the vendor goes bankrupt or fails to provide contracted maintenance.
So it's a safety net for business continuity.
Exactly. It ensures you could potentially maintain the software yourself if the vendor disappears. It's a business continuity control, not a security assessment tool. You don't get to look at the code in escrow just to check for vulnerabilities during normal operations.
Good clarification. Finally, many organizations are moving workloads to the cloud, using managed services. Does that eliminate these application security risks?
Not at all. It changes the risk landscape, but doesn't eliminate it. The cloud operates on a shared responsibility model. While the provider manages the underlying infrastructure security, the customer is still responsible for securing their own applications, data, and configurations within the cloud.
And where do things typically go wrong in the cloud?
Consistently, the top reasons for breaches involving cloud services boil down to user error or oversight. Number one is misconfigurations, things like accidentally leaving a storage bucket like AWS S3 open to the public internet, or having overly permissive firewall rules.
Simple mistakes, big impact.
Huge impact. Number two is lack of visibility into access settings. Cloud environments can be complex. Organizations often don't have a clear picture of exactly who or what has access to their cloud resources. And number three is improper access control at the application layer itself, the same kinds of broken access control flaws we discussed earlier, just now running in the cloud.
So the cloud provider secures the platform, but you still have to secure your stuff on the platform.
Absolutely. Configuration and application level security remain critical customer responsibilities. Hashtag tag, outro.
Wow, okay. We have covered a ton of ground there, from the initial security plan all the way through to managing third-party code and cloud configurations. That was a really thorough deep dive into building and maintaining trust in software.
It really is a cradle-to-grave process, isn't it? The key takeaway for you, the listener, should be that software security isn't really a separate discipline. It's fundamentally about quality.
Quality in what sense?
Quality in terms of design, aiming for that high cohesion and low coupling we talked about. Quality in terms of implementation, avoiding common coding flaws. And quality in terms of process, continuously checking and assuring that quality through testing and monitoring, ideally within a mature DevSecOps culture.
So security, quality, built in and checked continuously.
That's the essence of it. It requires that holistic approach, embedding security thinking into every stage.
And hopefully we've also clarified that important difference between the technical act of finding bugs through testing and verification
Versus the management responsibility of accepting risk, which is formalized through accreditation and requires diligent ongoing management, especially for those ubiquitous third-party components.
Right. That TPC management piece seems like a huge ongoing challenge.
It absolutely is. Which brings me to a final thought, something for you to chew on. Think about the risk posed by a third-party component in your environment that hasn't received an update from its vendor or community in, say, a year or two.
Even if there are no known CVEs for it right now.
Even then, our sources suggest, and it's a common view, that such components are effectively end of life, even if not officially declared so. They're orphaned. The risk isn't just known vulnerabilities. It's the unknown ones that might be discovered tomorrow, with no one actively maintaining the code to fix them. So the provocative question is,
How does your organization balance the very real cost and effort of proactively identifying and replacing these potentially orphan TPCs incurring that technical debt or migration cost now versus the potentially much higher, maybe even catastrophic cost of reacting when a devastating zero-day vulnerability is suddenly dropped for that component that nobody's touched in years.
That's a tough calculation.
Yeah.
Proactive investment versus reactive panic.
It's the heart of the modern application security budget dilemma, especially with software supply chains getting ever more complex. It's a risk acceptance decision with potentially huge consequences.
That is definitely something to think about, especially how to quantify that risk before disaster strikes. Thank you. This has been incredibly insightful, navigating the entire secure software landscape. My pleasure. It's a critical domain.
And thank you all for joining us for this deep dive. We'll see you next time.